Hey, I'm Rob Taylor, visual artist and general maker, and today we're in the shop looking at these two BR85 kits, the last two in the first run. These actually aren't going to be shipped out as kits, but they're going to be full builds. So I'm taking the opportunity to put together a few videos on what that process is going to be from raw kit to finished shippable product. Now there's a twist, because on these ones it's not just going to be assembly and painting. I also have to do some extra features on the original test build here. We're going to be lighting the ammo counter here. That's going to be using RGB LEDs because it's a specific color. And we're going to be lighting the scope as well. There's also going to be a mechanical component right here. We're going to have the charging lever rackable, just to make it look kind of cool at conventions. And we're also going to make the safety selector move, which will probably be in the same video as the sprung charging lever. So that's probably going to be 3 videos, and then I'll do the final one on the actual assembly and painting, as you would expect. So, yeah, let's get started. Okay, so here's one of the finished battle rifles. It's several months later, and in this video we're going to be looking at the ammo counter and how to build that, the whole structure inside right here. Obviously, statistically, you're not going to be building a battle rifle, but I'm trying to structure this video series so that you can extrapolate it into whatever you might actually be building. So with that said, let's get on. Okay, first things first, I made a paper template taking measurements directly from the resin cast, and you'll see how I did that a little later in the video. Having to dab because paper templates aren't that great, and Sharpies tend to kind of ruin the edges. You'll see me duplicate a bunch of stuff in this video because I was building 2 battle rifles at the same time, so I figured I would just do everything in duplicate. It made more sense. Cutting those out is relatively straightforward with a scroll saw. Working with acrylic is kinda messy using traditional techniques. It's not ideal. When you sand it like this, it actually melts it more than sands it. So you end up with this big burr on one side that you kind of have to peel off once it's like cooled and solidified. It's a bit odd, but it cleans up okay. The idea there is simply to trim it down to the measurements, and then we can actually fit it to the exact hole later on. And the end result looks pretty good. Alright, time to cut out the hole for the window to sit inside. Pretty much the only way I found of reliably doing this was to use a Dremel plastic cutting disc. It's kind of unfortunate because, yes, goggles are important. It's kind of unfortunate because the shank and the diameter aren't really designed for this kind of thing, getting into tight corners, but you just make the most of it, and then if you nick something with the chuck, then you just have to fill it in later. There I was measuring down the 32mm, that's the height of that window, and putting a line across that I could follow to really define the outline of the window, and make sure I didn't go past it with the cutting disc. You probably noticed the shop vac clamped to the table. This actually worked surprisingly well for the most part, and I'm considering building a downdraft table. This particular cast was a lot more difficult to do than the other one because the rotor casting didn't go so well inside. It was quite solid. When it comes to carving through solid resin, it's really just anything goes. There's no real technique to it. I mean, you can use a chainsaw if the project is big enough. I mean, that durability is super good, in terms of the long-term lifespan of the actual finished prop, but yeah, it can make life difficult when you're actually building it. Part of the problem was actually just simply the geometry of the actual part. Like, something that shape really isn't going to do well when it comes to rotor casting, because the gel curing resin is going to get stuck in one end, in all likelihood, and I'm pretty sure that's what happened here. So you've got to carve out not just the skin, but all that material underneath. Now, if you have a rotor casting machine, then you may not have that issue, because it's going to spin the material towards the outside, and generally just keep it moving sufficiently that it can actually just stick to itself in a fairly smooth coating. I think this specific instance, I didn't move it fast enough while turning it, and this is the end result. And eventually you end up with something that doesn't look too terribly horrible like that. And I poked a hole in it, yeah, where I used a drywall rotor zip bit to cut deeper into the material. Alright, now we have both a window and a frame to put it into, so it's time to make one fit the other. Just got to take into account parallax and refraction through the acrylic when you're doing this. But it's pretty straightforward, and the result looks like this. Pretty close. One end of the tube done, time to figure out the other end. With some rough trigonometry, we can get some approximate measurements for the strip board that's going to hold the LEDs. So the result looks like that, and now it's time to prepare the LEDs for soldering in. I couldn't get diffuse RGB LEDs from the supplier I used, so I just diffuse it myself by hitting it with some 400 grit wet and dry. Works pretty well. This is just so that we don't get hot spots on the screen. It gets a fairly even coverage as much as possible. Now, presumably for interests of space, the lights on these 5mm LED packages are not 0.1 inch standard pitch spacing, so we have to bend them out and then bend them back in at the correct spacing. Which LED you decide to use for the straight ahead one doesn't really matter, as long as it's consistent, because obviously all 3 LEDs have to be the right way around, or however many you're using. In this case it's 3. So as you can see, we just bend it out and then come in a little way and then bend it back in again. Gives it a nice cyberpunk look. Once we're pretty sure that the legs fit the pitch spacing, we can go ahead and solder it into place on our piece of already prepared strip board. I found that actually the tension in the way that the legs are bent holds it in upside down without having to use the other side of the helping hands, which is kind of handy. What we're actually doing here is pretty much literally building an LED strip. Now, some other projects, like maybe other sci-fi rifles where they have the light strips in the side, may need much longer strips, in which case it would probably be worth looking into commercial LED strips. But if the project needs a custom configuration, either shape or type of LED or whatever, then this would be the way to do it. The slight angle between them here is to illuminate the entire 32mm screen evenly and not have too much overlap between circles. Then it's just a case of trimming the legs off. In some circumstances, especially if you're using something like hot glue to cement it into the model, you may actually want to leave the legs on to act as anchors, as long as you're careful about short circuits. Time to solder on the power leads, using RGB for RGB obviously, and white for the common anode, because obviously I can't use red. Testing for continuity to make sure I haven't left any wisps of solder between the copper traces, causing short circuits. Common anode is where the positive rail gets shared between all 3 LEDs inside the package, and then the cathodes get broken out. Doesn't really make much of a difference unless you're doing digital circuits, in which case you would wire your microcontroller circuit differently. Tape it up to organize the leads and protect the solder joints, and we're good to go. Next, diffusing the screen. Diffusion's one of those things where generally the more of it you have, the better. Although too much and you will start losing significant amounts of light as it gets absorbed at each level. I'm doing both sides of the screen as well as the LEDs with 150 grit, and then follow that up with 400 just to make the surface a bit nicer, hopefully without affecting the deep scratches too much, with this nice sea glass result. Now the next set of measurements actually relies on the screen being there, so we've got to try and fit it as closely as possible to its final position. This isn't going to be an exact method of measurement, so the closer we get at each stage, the better. Got to rock the rule back and forth on the screen to make sure it's actually perfectly perpendicular. Then once the LED strip is in its final position, we can actually take the measurements required to put together the triangles we need to calculate the actual dimensions of the housing. Now I'm building it as a self-contained unit because, as you can see, the geometry of the actual cast really isn't conducive to attempting to align the LEDs in the screen or really hold them in place at all. It's really got to be something that I can actually attach to the entire thing as a large block to maintain that alignment that we need to ensure that the screen lights up properly. Here you're starting to see why all the finicky measurements were required. It's not exactly a square-based pyramid I'm building here. It follows the angle that the LEDs are sort of arranged in. If you remember the slight lean they had earlier, you can just about see there that they're sort of parallel to each side. Here I'm making my alignment marks on the sides where they actually meet with all the other parts of the unit, or will when it's complete. The sides aren't actually going to be solid for various reasons. Primarily that I'm actually going to be making them reflective, which is one of the main reasons why this had to be a self-contained unit as well, because obviously throwing aluminum sheeting inside that carry rail cast geometry really wouldn't work at directing light in any particular direction at all. So that's probably the main reason why all of this is necessary, actually. To avoid light loss through total internal reflection and general undesirable refraction, I'm trying to minimize the amount of acrylic in front of the LEDs, especially considering how wide an angle the now frosted lenses will be scattering light across. Fits quite nicely inside there, but up against the screen. Now, as I said earlier, it's not a simple square-based pyramid that we're building here, but it is slightly pyramidal, so we've got to slope the sides in. And to do that, we can just file down those edges at a slight bevel to try and bring them in a little bit. Then it's just a case of using acrylic cement to connect everything together, and we're good to go. I'm using IPS Weld-On 16, now called SiGrip 16. They changed the name. The number just denotes the exact thickness formulation. It's a pretty versatile range of solvent cements. With the main body built, it's time to start attaching the other end with the LEDs on it. The most logical way to do this, given that I'm going to cover the whole thing in aluminum tape anyway, is to use aluminum tape to rigidify the chassis and then partially attach the circuit board with that. Obviously, it's important to try and keep the tape as flat as possible while attaching it. The more crinkled it gets during application, the less consistent it's going to be in terms of reflectivity, and the light's going to get lost somewhere in the body of this thing before it actually reaches the screen. And of course, now that we have 3 sides on this thing, we can fill it with that most revered of costuming materials, hot glue. The idea is to tie the LED legs to those little extra holes that are drilled in the base right there, that I'm injecting it through right now. The whole thing should sort of solidify through everything and hold it together fairly strongly. And here's the actual structure complete. Not exactly the prettiest internals you've seen in your life, but until I get a laser cutter, they'll do the job. Now it's time to actually wrap this thing in foil and make sure all the light stays inside of it. As you can see, even being careful, it's pretty difficult to keep aluminum tape from doing whatever it really feels like, unless you're applying it to a completely rigid structure. On the other hand, it is fairly convenient to apply, relatively cheap, and for the purposes of the exercise, pretty reflective. Now, of course, this thing doesn't actually have a rigid beam along the top, so I kind of forgot that I would have to leave a space so that the LED could actually see the top of the screen. This part, with only pretty much 2 solid connections, took quite some time to complete. At one point I got so irritated and I actually considered cutting up and polishing individual plates of 16th inch aluminum to actually just build the structure out of, but I persevered eventually. In the end, the crinkliness you see here didn't actually seem to be much of a problem in terms of light output, and obviously presumably assisted with diffusion. Here I have power coming in through that resistor between the yellow and white on the breadboard into the common anode, and then through each of the color power output leads I have the preset pots down there that I'm twiddling to turn up and down each color. Since at this point this thing is basically complete, it can be trial fitted into its permanent home. Make sure the aluminum tape doesn't interfere with its press fit or anything, and generally give it a trial run. Here I'm only connecting the blue LED to the power source, so the light is far more blue than it will be when I finalize the color, because only the blue LED is actually lighting up. Obviously, if you only need perfectly blue light, then you wouldn't even use RGB LEDs in the first place. The whole point of this is to have some adjustability in terms of color. It's important to drive LEDs with constant current rather than constant voltage. That is to say, active feedback controlled voltage to maintain a specific current. This is because LEDs are variable, and supplying 2 different LEDs with the same amount of voltage may not result in the same amount of current draw. That will result in different brightnesses, different colors, and potentially an overdraw of current followed by diode failure. Obviously, this isn't an absolute, it's more of a preference. In reality, once you have your LEDs inside your model, they're going to be fed by, in all likelihood, a set of batteries through a current limiting resistor. As long as you are on the side of caution with the limiting resistor, then you should be okay. That means choosing a resistor to deliver a lower current to your LED than is its working current on its datasheet, with the voltage that you expect to be using, including taking into account the higher voltage of freshly charged batteries. I'm fastening the light unit in here with hot glue for 2 reasons. One being that there aren't really any connection points for any stronger glues like super glue or epoxy, and 2, it has some vibration resistance, which should hopefully help the whole thing from becoming detached if the gun gets jostled around. Here I'm attaching the resistors, a different value for each of the RGB, plus a higher value for the white V-in. I'm not going to go into how to calculate all those values, because that's a whole other discussion unto itself. It wouldn't be sensible to try and bring into this scope. But actually what I did here, rather than calculating it, is I used the preset potentiometers you saw earlier that I was dialing back and forth to simply get the color that I wanted out of the LEDs, and then measured the resistance across the pots. Because typically resistor values aren't all that important in electronics, and when they are, people just use preset pots. They don't actually manufacture every possible ohm value of resistor, so what you have to do is look up the values that you have with what the closest values are that are actually manufactured. So the values I got were 657 ohms on red, which became 680. 215 ohms on green, which became 220. And 255 ohms on blue, which became 270. Now, even though I was running a 9-volt battery on this thing, and therefore typically a 330 ohm power resistor would do the trick, I actually went wildly overboard, just simply due to the sheer impossibility of replacing these things if there's a problem. So I put a killer ohm resistor on V-in. Since the only place you can really get in to access the batteries to replace them and operate a switch or whatever is the back of the stock, we have to do a wiring harness extension. This will give it the length it needs to get down from the carrier rail through the barrel jacket, around the grip area towards the back, up and through the stock, along the inside of the stock to the actual battery compartment. At this point, this thing is actually complete. Yay! But in order to actually start assembly of the resin parts, it's gonna have to have some kind of base plate put in there that the epoxy can latch onto and make a better connection with the barrel jacket and chamber where it connects to. To do that, I'll be going back to that good old staple mat board. Easier to deal with than styrene, and easier to attach things to. This ease of use is the main reason I love mat boards so much. Its ability to be quickly marked and cut to shape and then trimmed to a perfect size is super handy when you're doing like quick on the fly stuff like this, and probably a major reason why it's used so much in prototyping and scale models and that kind of thing. This mat board's actually left over from where I matted my own work to frame it, so it was basically free, but it's pretty cheap. You can get a huge, like 40 by 30 or something sheet of it for maybe 20 bucks. It's not bad at all. Now, what I would probably have preferred to do in this instance is actually not use mat board and instead use a 2-part expanding foam and just poured that into the cavity to support the Bondo. But I don't actually have any, and I didn't really want to use a can of spray foam on one small part, so I had to go with the next best thing. At this point, it's just a case of trimming up the hot glue so that the entire surface is flush, and then we can get on with Bondo. Now, I'm not going to go too much into this because I have an entire blog post dedicated to looking at the Bondo workflow, called, funnily enough, the Bondo workflow. And I go through every step of the process in there, from selecting your tools to mixing to trimming, finishing work, everything. So there's no real reason to duplicate that in 40 seconds here. This kind of skim coating work is a little bit tricky with Bondo, but as long as you let it harden enough between coats, it's usually okay. If you don't let it harden enough, then when you come to trim off the excess, scrape it flush, then you actually just end up peeling it all back off. And sometimes whatever's underneath with it, depending on if it's soluble in polyester resin. Now there's enough solid material there to get a good connection. All that remains is to paint the edges that'll be hidden by a pretty severe undercut once it's assembled. Alright, that's it. I hope that was interesting and informative and maybe even fun. Thanks for watching. If you have any questions or comments, hit me up below, or I guess social, maybe in here or something. Next time we should be looking at the charging lever mechanism. Should be good for other stuff as well. And yeah, thanks again for watching. Catch you on the next one.